When we were discussing horizontal asymptotes, we made a note that in the case of rational functions where the degree of the numerator was greater than the degree of the denominator, there's no horizontal asymptote. But is there something that we can talk about the end behavior of such functions where the degree of the numerator is greater than the degree of the denominator? Let's investigate. We may recall from middle school that in the case of rational numbers, when you have a numerator over denominator, you can express it as q plus r over d, where that r represents the remainder and q is the quotient. Okay, so something like 141 over 8, I worked it out, is something like 17 plus, is it 5 over 8 or something like that? Okay, I think it's right. Okay, so that remainder is actually greater than or equal to 0. Let me bring that, and it is strictly less than that d, all right? That's the condition. What would happen to rational functions where the degree of the numerator is greater than the degree of the denominator? And the degree of the numerator being greater than the degree of the denominator means that we can divide them, right? We can divide fx over g of x, and then we should be able to write it as some q of x, the quotient function, plus some r of x, the remainder function, divided by g of x. In the same way, right, as we did for numbers, we should be able to get some kind of a similar expression. And what does that tell us about q of x, the quotient function? Let's explore this using a particular example. So here we have a rational function where the degree of the numerator is 2, as you can see, and the degree of the denominator is 1. So clearly there is no horizontal asymptote. I'm going to use the calculator to perform this division because this is an exploration, and you can study about synthetic division and long division of polynomials in some other video, but this we are trying to explore something, and so we can use technology for our exploration. When I hit enter, I get the result as 45 over x plus 3 plus 4x minus 16. Let me just copy that down, and I'm going to write it as, I get 4x squared minus 4x minus 3 over x plus 3. That was the question. That's the numerator over denominator. I'm going to write it as, what do I get? The quotient was 4x minus 16, and the remainder over divisor was 45. That's the remainder, x plus 3. Can you see that? Can you see that? Can you see the connection between n over d is equal to q plus r over d, that same d, all right? So you can see that this is the same term here, and this is my quotient function, and that's my remainder. I'm going to continue this exploration on our calculator. So I'll start by defining f of x, control the key to the right hand side of 9, and I'm not going to bother typing. I'm just going to just copy that. So f of x is going to be that rational function defined, right? Done. And I'm going to call r of x as, not r, q, sorry, q of x as a quotient function. Okay, so control the key to the right hand side of 9 as a quotient. And this was our quotient, okay, 4x minus 16. Copy, paste. There we go. Done. So f of x is the original function, the rational function, and q of x is equal to 4x minus 16 was a quotient when you divide 4x squared minus 4x minus 3 by x plus 3. All right, let's insert a graphing page now to continue with this exploration. I'm just going to type in f of x, all right? And that should graph, that's a graph of the rational function. And I'm going to hit tab, and I'm going to say q of x. Is that what we defined? Yeah. And that's my quotient function, all right? At the moment, we don't see much, so let's bring in our table. And what we are going to do is split screen table. There you go. So now with the table, we have x values, f1x representing the values of the rational function, f2, the quotient function, okay? So there's not much we can see initially. So what we'll do is that let's just go and make some changes to the table settings. Let me start the table at 100. Table step at, let's say, 50. That means it's going to, the increment value is 50. And let me just hit OK and see what's going on. All right, 100, 150, the x values, and these are the rational function values, corresponding values here. Whoa, whoa, whoa. At 100, f1x is 384.436, whereas this is 384 point whatever, but it's still close. 584 at 150, 584 there. And let's move down, guys. At 500, let's look at the values for 500. The rational function is 1984.08, whereas the quotient function is 1984.00. All right. This is interesting. So when I go all the way to, let's say, 1000, at 1000, my rational function was 5984.04. And this is, did I read it correctly? What did I read? Okay, it's 3984.04. Whereas the quotient function is 3984.00. Wow, that looks promising. Let me just go to all the way to what, 6000? And at 6000, the rational function is 23984.0 up to one decimal place. I don't know what's happening. What's the next one? 23984.007 and whatever. Okay, that's the rational function. But at the same value of x equals 6000, the rational function is 23984.0. Wow, that's interesting. Just to make it more interesting, let's go back to the calculator page, and I'm going to say f of, let's make a really large value. Remember, x being a really large value is actually talking about x approaching infinity. That was the idea. Large values. Let's hit enter. Should we put 2 more zeros? Okay, 2 more zeros. I'd put 3. That's okay. X approaching large values. Hit enter, but I'm going to hit control enter so that I can get a approximate value. There we go. So 3 followed by how many 9s and 84.0. Okay, let's check the Q for the same value. I don't know whether I'm going to make a mistake entering the numbers of 0. So I'm just going to copy that, paste it here. And again, when I hit control enter, what am I going to get? Wow. Wow. This means that numerically, the value of f of x, which was a rational function, numerator being, the degree of the numerator being greater than the degree of the denominator, the value of that rational function at a large value of x is equal to or almost equal to the value of a linear function. 4x minus 16 is a linear function at that same value of x. Let's look at the table again. Again, this is a numerical comparison, guys. Numerical investigation, numerical method of investigating. We saw at 6000 and I just, went crazy and I went up to x approaching a large value. And you can see that numerically that the rational function is almost the same y value as the graph of the linear function. Let's take a look at it, what happens through the graph. So what I'm going to do is that I'm just going to close this table, okay, so that we can see the graph more clearly. So I'm going to go to table and remove table is not deleting the table. At the first glance, this is x values from -10 to 10 and y values are going from -6 to 6. I'm just going to make those changes there so that, we can see a little bit of what's going on to the graph because we are interested in the end behavior. So let's make the window setting slightly different. I'm going to make xmin as -25 to 25, xmin and xmax, and the scale, I'm going to change that to 5, okay? No, 5 I said. And ymin and ymax, I'm going to make that -150 as the minimum value of y. And the ymax value, I'm going to make it 50. The increment for y, I'm going to make that 25. And let me just see what's going to happen, okay? Whoa. Graphically, you can see that after some values, the blue graph and the red graph are almost running parallel, almost like a straight line. The red line, of course, was the quotient function. That was the equation of the straight line. 4x minus 16, something like that. 4x minus 16. But the blue graph was a rational function with a degree of the numerator being greater than the degree of the denominator. And you can see that after some values of x, x equals 6000 onwards, we saw that the rational function's values were almost identical. And the other cool thing is that even for values on the negative side, negative infinity, as you go to large negative values, the values of the blue graph, the rational function, do come closer and closer to the linear function. What this means is that as x approaches large values, both on the right-hand side and on the left-hand side, all right, so negative infinity and positive infinity, this rational function where the degree of the numerator is greater than the degree of the denominator, so we can say 4x squared minus 4x minus 3 over x plus 3 approaches or behaves identical to a straight line whose equation is 4x minus 16. Likewise, on the left-hand side, right? So 4x squared minus 4x minus 3 over x plus 3 behaves identical to 4x minus 16. That means that the end behavior of this rational function is identical to the straight line. But the straight line, notice what's so different about this straight line compared to the horizontal straight line or the horizontal line that we saw when we talked about horizontal asymptotes. This one is not horizontal. This one has a slope. This one has a slope, which means that the end behavior of this rational function, where the degree of the numerator is greater than the degree of the denominator, is a non-horizontal straight line. And these non-horizontal asymptotes are known as slant or oblique asymptotes. Interesting, huh? Oblique, slant. Let's just quickly go through what we explored so far. So we were looking at a rational function. So this particular rational function, where the degree of the numerator is greater than the degree of the denominator, as x approaches large values, will not have a horizontal asymptote. In fact, it will also increase, and it will increase according to this pattern, the pattern of this straight line, because even 4x minus 16 as x approaches large values will keep increasing without bound. So this will also increase, but the pattern of its increase is almost identical to this straight line with equation 4x minus 16. But there's one more thing that we need to take note of. This term on the quotient, the degree of that term is 1, being linear, all right? So the degree of this term is 1. Whereas on the left-hand side, the degree of the numerator is 1 more than the degree of the denominator. Just 1 more than the degree of the denominator. Okay, just keep that in mind. On the left-hand side, we have the degrees in such a pattern that the degree of the numerator is 1 more than the degree of the denominator, whereas on the right-hand side, the degree of the quotient is equal to 1. Let's make a note of that, and let's try and take a look at another example to make a connection with this observation. This observation meaning regarding the degrees, all right? Ready? Our second example is another rational function where the degree of the numerator is 3, the degree of the denominator is 1, and so again a case of degree of numerator being greater than the degree of the denominator, so it doesn't have a horizontal asymptote, meaning doesn't have a finite limit. And in this case, to structure our exploration, we're considering the case where the degree of the numerator is 2 greater than the degree of the denominator. So just as before, we are going to use the calculator to perform our division. This is an exploration. Like I said before, we do not want to spend too much time doing synthetic division. Control, division sign. I think these are the good things of technology, in exploration, you can use the CAS because of the CAS, I'm able to do all this. Otherwise, you'd be spending too much time doing all the other algebra, which is nothing wrong. It's just that the focus of the exploration is a lot more than the algebra, right? You shouldn't get distracted. So here I have entered my rational function and I hit enter. So that's my result. 22 is the remainder, and this is my quotient. And this time, as you can see, the quotient is a quadratic expression, 2x squared minus 9x plus 4. So maybe that is one of the first observations you need to make, that when the degree of the numerator is 2 more than the degree of the denominator, the quotient after division is going to be a quadratic, degree 2 compared to degree 1 in the first case, okay? Make those kind of observatory notes, which means that I can write this rational function now as this was 2x cubed minus 7x squared minus 13x plus 18 divided by x plus 1 is equal to, I'm going to write the quotient first, okay? And I'm just going to make sure that this is in the view of the camera for all of us to see. This is 2x squared minus 9x minus 4, that's a quotient, plus 22 over x plus 1. This was that n over d is equal to q plus r over d. All right, just comparing with that. So this is our remainder, and that's our quotient. We are interested in comparing this one and this one. Ready? So back on the calculator page, I'm going to define my rational function as, by just copying down as I did before, okay? There you go, that's done. And why not use all these features? Because, like I said, it's not just the algebra, but also, because it's an exploration, our focus should be something else. And if all these features are possible on a calculator, then why not? Okay, copy, paste. We've seen it in the other videos. There you go. So I have defined two functions while I was, trying to do all that. So this is our f of x, our rational function where the degree of the numerator is greater than the degree of the denominator, but it's greater by 2 this time. And the quotient, it's a quadratic this time. Okay. So what did we do next? We added a graph page to see the behavior, right? So let's go and check these on the graph page. So I'm going to have f of x graph as it is, and that's an interesting function. Let's move the label somewhere else. Whoa, no, it's behaving. All right, behave. And I'm going to hit tab. I want the quotient also. Okay, hit enter. The quotient is also graphed in some way. And perhaps by looking at the graph, we can't say, because we are interested in the end behavior. Remember, as x approaches large values, and these are smaller values around 0, okay, on the left and the right hand side of 0. So let's go back to our table. All right, so I'm going to go and see what's going on at the table. That's a good way to compare. Numerical approach. And these are the initial values of x, f1 representing the rational function, and f2 representing the quadratic this time. Okay, what do we have as we keep going on? Is there something to agree upon? Let's just jump and see what happens for large values. All right, so let's go and see when we edit the table settings starting at, let's say, 100 like we did before, and the table step size at 25. That should be good. Let's just go and check this out. So at 100, x equals 100, the value of the rational function was 19096.2. The exact value is here somewhere here, 2.217, so on and so forth. And when I just go to the right and see, okay, 19096, what is it there? Oh, same. Well, similar, because this is 19096.00 and this is 19096.2. Wow, that says something. That says that x equals 100. Let's just scroll down to x equals 500. Is that what we did? Okay. Here, the value of the rational function is 495,496.043. And the corresponding value here is 495,496.04. No, that's, I was literally very excited at that point in time. Anyway, let's go down to maybe 500 we saw, right? Let's go down to 1000 this time and check what's going on. At 1000, x equals 1000, the value of the rational function is 1990996.02. And at that same value, we got 1990996. Something is going on. Let's do the same thing that we did in the earlier case. We're going to enter a large value, all right? F of large value, all right? And I'll hit Control Enter to get the approximate value. This is 1.999999, and that's 10 to the power of whatever, 18, because you know what? It's increasing without bound, right? So let's do the same thing with Q. And I want the same large value. So this time again, I'm going to copy and paste that in here. And when I say Control Enter, what am I going to get? Fingers crossed. Wow. That is something. Now, what does that mean? That means that when as x approaches large values, remember we're talking about large values, the behavior of this rational function is the same as the behavior of this quadratic function. That as x approaches large values, 2x cubed minus 7x squared minus 13x plus 18, I hope I got all that right, tends to 2x squared minus 9x minus 4. There we go. I hope we can bring all of this onto our screen there. There you go. Okay. So this is remarkable. This is like saying for large values of x, this rational function is going to have values that are identical to the quadratic. Now, it still means that it's going to grow to infinity. That means it's going to grow without bound, but it's going to grow in the same way, in the same manner, in the same pattern like this quadratic. Let's take a look at what's happening to the graph of these two, the rational function and the quadratic. So I'm going to go here, close the table, meaning remove the table. I'm going to go and adjust the window quickly. This is, let's make it negative 10, 10. Scale can be 1, y min negative 50 maybe, and y max can be 150. This can be, what can this be? This can be 5 perhaps. Let's just check what's happening. Whoa, take a look at that. Take a look at that. The blue graph is our rational function, okay? And remember that the degree of the numerator was differing by 2, by 2. And the red graph is our quadratic, the quotient, okay? And even here for large values of x on both sides, x approaching positive infinity and x approaching negative infinity, you can see that the blue graph, the rational function, and the quadratic, the quotient obtained when you divide the numerator by the denominator, they both seem to agree. Yes, they both are increasing, they increase without bound. There is no finite limit as in the case of a horizontal asymptote, but still there is a very interesting observation to be made that the rational function behaves just as this quadratic function as x approaches infinity. That's interesting. And this asymptotic behavior of this particular rational function is interesting because now we have a case where the asymptote is non-linear. See, vertical asymptotes, linear. Horizontal asymptotes, linear. Slant asymptote, also linear, although, it's not a horizontal or a vertical line, it's got a slope. But now we have just seen that an asymptote can also be non-linear. What? A non-linear asymptote? Is there even such a thing? Or are we getting ahead of ourselves? Let's take one more case before we generalize. So this is a third case of a rational function where the degree of the numerator is greater than the degree of the denominator. And let's compare what we have here. The degree of the denominator is 2. The degree of the numerator is 5, which means the degree of the numerator is greater than the degree of the denominator by 3. Okay? Now, any guesses what the degree of the quotient is going to be in this case? I'm not going to go through the entire exploration because it's going to become a very long video, but I've done everything for you on the calculator. So when the degree of the numerator is greater than the degree of the denominator by 3, we get a cubic quotient. And as you can see, I've already gone ahead and defined fx and qx as accordingly, and even gone to verify that for large value of x, for a very large value of x in behavior we were talking about, both the rational function and the quotient function seem to agree. And not only that, even on the graph, you can see that the rational function, which is in blue, and the cubic function, which is in red, seem to agree for x approaching infinity, positive infinity, and x approaching negative infinity. So what can we conclude from all of this? Let's make a little chart, maybe that'll help us, okay? Now, when the difference of the degrees means the degree of the numerator being greater than the degree of the denominator, okay? When that difference was 1, we saw that the quotient was of degree 1. So degree of, I'll call this degree, is it visible? Yeah, degree of the quotient was also 1. When, and we call it a slant asymptote, right? Slant or an oblique asymptote. All right, when the difference of the degree, that means when the degree of the numerator was greater than the degree of the denominator by 2, we got the degree of the quotient to be 2. We got a non-linear, a quadratic asymptote. And then when the difference, the degree of the numerator was greater than the degree of the denominator by 3, we got the quotient as a cubic polynomial expression. And that again seemed to be an example of a non-linear asymptote. All right, there's too many things now written in front of me. So let me just try and see whether I can move it away. Here we go. All right, the question that I want to leave you all with is this. What then is an asymptote? What do you understand by asymptotic behavior of a function? Let me know in the comments below, and do not forget to subscribe to my channel. I'll see you in the next video.